Engineering 305, Chapter 7, Section 7, Shear Stresses in Beams. This really needs to have a nice in-class demo to go with it. Unfortunately, I will not be there tomorrow or for the near future. The goal from this section is really the extension of 18, calculating normal and shear stresses. These are the transverse shear stresses in beams, so this is a little bit different. And we're going to wind up with some different equations for this. We're going to actually wind up with a collection of 3 shortcuts. Those equations look like this. Right off the study guide, we get a formula for the shear stress. Hey, guess what? My pen's not working. We're going to wind up with an equation for the shear stress in rectangular section beams, I-beams, and then circular sections. And you'll see why we use those in a little bit as shortcuts, because we really don't want to do it the long way. So the first thing that we need to remember around this topic is that strain is linearly distributed from the neutral axis. That at that neutral axis, let's see if I can draw this. If I've got the end of a beam and then there's my neutral axis, my strain is going to go like this. Stretch, 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 such that I get the most strain farthest away, and these are where I get the tensile and compressive stresses. But when I have a system that is not homogeneous in Y in terms of its geometry, for example, let's look at an I-beam. Then while this is straining a lot, that also has a bunch of the stiffness of the section, and then that changes the way that the shear gets distributed. So this becomes a very complicated, well, it's a kind of a complicated equation. Let's show you what that is. For the equation for the transverse shear looks like this. The shear is the limit as x goes to 0 of the moment, how the moment changes in x. And then this has already been, I hope you can see, it's already been massaged a lot because I've got that I. Remember that I is really the integral of y squared dA. Well, so this has already been massaged a lot, and so I get to this formula coming out the backside there, and we can make some further simplifications. dm dx, that's actually, and you may have kind of figured this out from the last section, that's just the shear, or sorry, that is the shear load that's taking place at that section. So this becomes, it becomes minus v over it, and then I've got this other term here, and this is where, again, more calculus, we define this geometry term as q. Q is equal to the integral of the thickness times the height from the neutral axis dy. I have to integrate that. But here's the kicker, and it's the limits of integration. You have to integrate from the height that you're looking at all the way to the extreme section, all the way out to C. And so every time you're going to do this, you're going to launch a new integration. And people just kind of say, yeah, I'm really not that interested in that. And so they looked at some generic shapes and they formulated some, hey, these are pretty good answers for the maximum shear, and then let's work with that because that's our worst case scenario. And I've talked to you about how engineering is getting away from being an exact answer to we're going to use some approximations so that we can move through our job quickly. So here are those simplified equations right off the formula sheet. We've got the shear for the rectangular section, which is 3/2 v over a. Now, compared to all the calculus that we were looking at, everything else, that is an equation I can live with. That one does me fine. For an I-beam, um, they give us an equation for the average shear, which is V over A, which is interesting because in one sense they're saying we're going to ignore the flanges, just look at the web as the rectangular section that we're using in the first equation, right? But then it's only, this is equal to 2/3. Maybe I should have put my equals a different spot. It's equal to 2/3 the shear for a rectangle. So that's, okay, that's interesting, but maybe not that important. That average shear for an I-beam is just that shear force divided by the area of the web. Just ignore the flanges. And then lastly, for a circular section, we're looking at 4/3 V over A. So this is even, this is somewhere in between the two, right? We don't have the flanges to throw out, but we don't simplify it with a 2/3. It's somewhere else. So it's a little bit higher than the beam, but it's a little lower. It's a little lower than the rectangular section. So, and in that sense, you've got some guidelines there about boundaries and what you should use. And if you forgot everything else, if you took your equation from an I-beam, just did V over A, even though it'd be completely incorrect, and you put a little fudge factor on it, like 1.5, hey, look at that. Everything is below that, and it's only, I know. But we're in this area where engineering has become art. It's no longer exact, and we all struggle with that a little bit. But we don't want to do the calculus. To really benefit from this, to really understand it, we've got to go to doing example problems. And so I'm jumping to example problem 710, where we'll start to see what this looks like in practice. And then we'll go, yeah, I'm pretty good not doing the hard stuff, maybe, and just taking the answer. And maybe not. Maybe you'll say, no, I'm going to work in aviation, and I want to know exactly what that answer is. So we'll do example problem 710 next, and we'll enjoy it. Don't worry, there's more to come. I'll see you guys when I see you.